This is section 6.1, Properties and Attributes of Polygons. The objective of this lesson is to classify polygons based on their sides and angles, and find and use measures of interior and exterior angles of polygons. Let's get started. You may recall in Chapter 2 we learned the definition of a polygon. So let's review that. It's a closed plane figure formed by three or more segments such that each segment intersects exactly two other segments only at their endpoints, and no two segments with common endpoint are collinear. Okay, so here is a diagram of a polygon. It is a closed figure. It has more than three segments, and those segments intersect only at their endpoints. So let's use this figure to talk about the different parts of a polygon. First, we have a side. Those are any of the segments that form the polygon, are called sides. The vertex is the point where two sides intersect. And we have the diagonal. It is a segment that connects any two non-consecutive vertices. So here I have a segment connecting vertex A and vertex D. These are not next to each other, so they're non-consecutive, so that would be called a diagonal. Another diagonal would be segment AC. We could also have a diagonal from B to E or B to D. Okay, so these are segments that connect vertices that are not next to each other. Polygons can be classified in several ways. First, let's talk about how they're named. They're named by the number of sides that they have. Pay attention to the prefixes of these names. Some of them will be familiar to you and you've used them many times before, but some may be new. You do need to remember them and be able to name polygons based on the number of sides that they have. So for a three-sided polygon, those are called triangles. Four sides are called quadrilaterals. A five-sided polygon is a pentagon. Six sides is a hexagon. Seven is a heptagon. 8 is octagon. 9, nonagon. 10 is a decagon. 11 is an undecagon. And 12 is a dodecagon. And beyond 12, just say n sides, whatever that n may be, we just call that an n-gon. So a 20-sided polygon would be called a 20-gon. Okay, so let's use those names and identify whether these figures are polygons, and if so, what is their name based on their number of sides. Okay, for the first one, it is a closed figure. The segments intersect only at the endpoints, and there's three or more, so that it is a polygon. And then since it has five sides, it's called a pentagon. For the second one, this would not be a polygon. These segments don't intersect only at endpoints. We have an intersection point here, not at an endpoint, so that would be not a polygon. For the third one, it is a polygon. We have 1, 2, 3, 4, 5, 6, 7, 8 sides. So if it's an 8-sided figure, it's called an octagon. And for the fourth one, we have a problem here. It's not closed. And that's part of the definition. It has to be a closed figure, so that would not be a polygon. Okay, take a minute, pause the video, and name these three shapes. Determine if it's a polygon, and then name it if it is. Okay, you should have gotten that the first one is not a polygon because we have this part here that is not a segment. It is a curve. They all must be segments. we have a hexagon, which is 6 sides, and a heptagon, which is a 7-sided polygon. A polygon is considered a regular polygon if it is both equilateral and equiangular. Remember, equilateral means all of the sides are congruent, and equiangular means all of the interior angles are congruent. So this would be a regular pentagon. One more classification we use is whether it's concave or convex. A concave polygon is a polygon in which a diagonal can be drawn, and part of that diagonal is in the exterior of the polygon. So in this example, or this diagram here of a concave quadrilateral, if I can draw a diagonal and any part of it is in the exterior or outside the figure, then it's called concave. And it may look like part of that shape or part of the figure has been caved in. We call that concave. For a convex polygon, no diagonals contain any points in the exterior. So drawing these diagonals here for this quadrilateral, both of them are inside the figure. No part of the diagonal is in the exterior. So that would be convex. Let's get some practice classifying polygons. I want to tell whether the polygon is regular or irregular, and concave or convex. Okay, for the first one, in order for it to be regular, all the sides have to be equal, and that's not the case here. So it's going to be irregular, and if I drew all the diagonals, I would see that all of them are inside the figure, so that's going to be convex. In the second figure, we have all the sides are congruent, all of the interior angles are congruent, so that's going to be a regular polygon, and all regular polygons are going to be convex. If you wanted to check, you could draw the diagonals and show that they all do remain inside the diagram. And you could do all the diagonals from all the vertices. Okay, looking at my third figure, I see that it goes in. Looks like it's caved in on some of these sides, so that's going to be a concave polygon. You can look at the diagonals as well. Here's one diagonal that's inside, but if I check this diagonal, there's part of it is on the outside or exterior to the polygon. So that's going to be concave. Also, checking to see if it's regular or irregular, all the sides are congruent, but not all of the angles are congruent. In fact, I only see 4 angles here that are shown. Since it's 8-sided figure, it should have 8 angles, but because it's concave, these other interior angles end up being greater than 180 degrees. So not all the angles are congruent, so it's an irregular concave polygon. And then in the last one, I see I have this part that goes into the figure. Here I can draw a diagonal that is exterior to the figure, so it's concave, and all the sides are not congruent and all of the interior angles are not congruent, so that's going to be irregular. Okay, take a minute and try these on your own and then check back and see how you did. Okay, you should have gotten that. The first one is a regular convex pentagon. The second one is an irregular convex quadrilateral. And the third one is irregular and concave. Okay, let's move on to finding the measures of interior and exterior angles of polygons. We're going to start with the interior angle measures of polygons first. The polygon angle sum theorem tells us that the interior angle measures, so all of the angles inside, of a convex polygon with n sides is going to be equal to n minus 2 times 180 degrees. Let's see what that looks like. Let's take a triangle. We actually already know that the interior angles of a triangle add up to 180 degrees. So let's use this formula that they give us and make sure that that's still true. Okay, we know that a triangle has 3 sides. So for a triangle, n is 3. We're going to use our formula and plug in 3 for n. So I end up with 3 minus 2 times 180 degrees. So the interior angle sum is 180 degrees, which I know is true because for a triangle that's always true. Let's use this formula for a quadrilateral. In a quadrilateral, we have 4 sides, so n is 4. So using our formula, substituting 4n for n, 4 minus 2 is 2, so I have 2 times 180 degrees, which is 360 degrees. So in this one, our n is 5. Using our formula, substitute 5n for n, and I get 3 times 180 degrees, which is 540 degrees. We can use that formula for any size polygon. In this example, we're going to find the value of c for this quadrilateral. Okay, these are all interior angles, and I know from the theorem before that all of the angles add up to n minus 2 times 180. So let's see what that sum is going to be. Using our formula and the fact that we have 4 sides here, so I'll substitute that 4 in. I get 4 minus 2, which is 2, or 360 degrees. That's what all of them added up will be. 360 degrees is going to equal c plus c plus 3c plus 3c. They're going to all add up to be 360. Just combine my like terms. When I divide by 8, I get c is equal to 45. And the polygon exterior angle sum theorem tells us that the sum of the exterior angle measures, okay, one exterior angle at each vertex, is going to be 360 degrees. So no matter whether it's a triangle, a pentagon, a 20gon, whatever it is, if it's a convex polygon, the sum of the exterior angles will always be 360 degrees. Let's use that in a couple of examples. Here I have a polygon. It's a quadrilateral, it's 4 sides, and I have all of the segments extended so to show the exterior angles. And I want to know what those exterior angles actually are, their measure. Well, I know that for any polygon, all the exterior angles are going to add up to 360 degrees. So that's where I start. So when I simplify that, then I can divide by 18, and I find that A equals 20. So now I know what A is, I can go back and substitute that back in. So instead of 6A, this angle measure is going to be 120 degrees. 7A will be 140 degrees. 3A is going to be 60 degrees. And 2A is going to be 40 degrees.